Hello guys, today we'll continue our discussion on PN junction diode and its biasing. This is what we have discussed in the last video. The PN junction functions under two different conditions. One is no bias or without bias and the second one is with biasing. Further, we have already discussed about this condition in the previous video. Today we'll be discussing on with biasing. Biasing of a PN junction diode can be done in two ways. One is forward biasing and the second one is reverse biasing. So let us start with forward biasing of PN junction diode. This is the PN junction diode and this is the potential barrier, and here these are the majority carriers, that is electrons on N side, and holes are the majority carriers on P side. What is the meaning of this forward bias? Anyway, biasing means we are applying some external voltage, right? And what is forward bias? Forward bias means the P region, this is the P side, that should be connected to the positive terminal of the applied voltage, and this N side should be connected to the negative terminal of the applied electric field or applied voltage source. So this is the connection. P side is connected to the positive side of the battery and the negative terminal of the battery is connected to the N side of the PN junction diode. Let the value of this potential is equals to Vf. This F denotes that this is a forward bias. Now we are having two potentials. One is the barrier potential V0 and one is the applied potential Vf. Looking into the electric field due to these potentials, this is V0. So the electric field will be equals to E, and the direction is from this positive side to negative side. So this is the electric field or the internal electric field due to this barrier potential. Now this voltage whatever we have applied over here, that also gives some electric field. So that electric field I have taken as EA, that is the applied electric field, and here this is the positive side, this is the negative side, and hence the direction of the applied electric field is from P side to N side, and the electric field direction due to this potential barrier is from N side to P side. That means the direction of applied electric field is opposite to that of the internal field. If I am applying some voltage, then what will happen to this junction? Here these electrons are negatively charged carriers and this side of the applied battery is negative. So the electrons, they will experience a repulsion from this negative side of the battery. If you are getting repulsion, they will move from N side to P side. Similarly, these holes, they will also get a repulsion from this positive terminal of the battery. So they will move towards the N side. Once the carrier starts moving from one side to other side, the width of this depletion layer, it starts decreasing. If we will increase the value of Vf little more, this width will decrease further. The width of depletion region decreases with increase in applied field. Now if the width is decreasing, what will happen to this barrier height over here? That will also decrease. Earlier it was V0, now it reduced to V0 minus Vf. That means the height of the potential barrier decreases. Thus if I am increasing the value of Vf, this width will go on decrease and finally it will disappear. Once this is disappearing, then there will be free flow of carriers from one side to other side. These are the electrons, they can move freely to P side because that barrier is no more there, right? No one is there to stop them. They can move freely from N side to P side, and these holes, they can move towards N side. So if there is a free flow of carriers, what will happen to the current? That will increase. So once the applied potential crosses the barrier potential, the current increases exponentially. When Vf is less than V0, there will be some barrier height over here. So it will be difficult for the carriers to move from one side to other, and hence will not be getting any current. But once this Vf is equals to V0, this will be aligned over here. And after that there will be free flow of carriers, and hence the current also increases. And why it is increasing exponentially, we will look into that. Under this forward bias, the diffusion current is much larger compared to drift current. Here, this is you and this is one of your friend. You are standing far apart from each other, but you want to speak something secret to your friend. So both of you need to come closer. Let now your distance is x unit. If you want to come closer, that means this distance should reduce. Let the reduced distance is x minus y. How can this distance x will become x minus y? The only way that both of you should come closer, right? We will be considering similar situation while plotting the energy band diagram for a PN junction diode under forward bias. So this is the energy band diagram when there is no bias, right? So when there is no bias, the distance between the conduction bands on P side and N side, what is the relative separation? This is EV0. While we are applying some forward bias, what is happening to this V0 value? It is changing from V0 to V0 minus Vf. If V0 is becoming V0 minus Vf, what will be this separation? This will be equals to E into the potential, and the potential is now V0 minus Vf. So what will be this separation? That is equals to EV0 minus Vf. Earlier it was EV0 when we have not applied any voltage to the diode, and after applying a forward biased voltage, the separation between the energy states reduced by an amount EVF, and the separation is equals to E into V0 minus Vf. If this will be equals to EV0 minus Vf, this height will increase or decrease? Definitely it should decrease. The similar situation what I have shown you just now, you want to reduce the distance between you and your friend. Here also this p-type band structures and n-side band structure, they want to reduce the distance between them. Then where should they move? Right, they should move towards each other. So towards each other means this is at a higher side, and this side, this red one is for n-type. So this is at a lower energy, you can see. So if they move towards each other means this should come down, and this side, this should go up. Earlier the formulable was aligned, but now there is a shift in the energy bands. So this will come down, this will go up. So this side Fermi energy, that will go up, and this side Fermi energy, it should come down. Here you can see this energy bands on n side, they are going up. So this is the formulable. Earlier both of these are aligned. Now it has shifted up, and this side it has shifted down. This is the new positions for the energy levels when a PN junction diode is under forward bias. Earlier the formulable was same for both the sides, P side and N side. Now I have written EFP is the position of the formulable at P side, and EFN is the position of formulable on N side. So the difference between these two is equals to ECN minus EFN, and here it is EF minus EBP. And what is this difference in energy? That is equals to EV0 minus VF. Looking into this, can you tell me what is the net amount through which the energy bands get shifted. So the relative displacement is equals to EVF. So earlier the separation between these two was 0. Now they are separated by an amount EVF. Now let us look into the PN junction diode under reverse bias. This is the PN junction diode. Under this reverse bias, what we are doing? We are connecting the P side of the diode to the negative terminal of the applied voltage source, and the N type should be connected to the positive terminal. P region is connected to the negative terminal and N region is connected to the positive terminal of the DC voltage source. Let the value of this applied potential is equals to VR. The electric field due to this barrier potential is from N side to P side, which we have seen. This is the positive side, this is the negative side. So the electric field due to the applied potential is from N side to P side. This is also from N side to P side. In the previous case, both are opposite to each other. Now both are in the same direction. That is, the applied electric field and the internal electric field are in the same direction. Now let us look into the carriers. What is happening to the carriers? The majority carriers on N side are electrons and the majority carriers on P side are holes, right? Now this positive terminal of the battery is connected to this negative side of the PN junction diode, and the electrons, which are the majority carriers, they are negatively charged. And if this is positive, what will happen? These electrons, they move towards this positive terminal of the applied voltage source. If these electrons are moving towards right, that means more and more immobile ions will be here, and hence this junction will shift towards right. Similarly, at the P side, if you see, this is the negative terminal which is connected to the P side. That means these holes, they will start moving towards this negative terminal. If they are moving away from the junction, definitely this junction will shift towards left. That means the width of the junction is increasing. If the width of the junction is increasing, hardly any carriers can cross this junction. If the depletion region width is increasing, this barrier height will also increase. Here both the potentials, they are in the same direction. So this height became V0 plus VR. Without bias, it was V0 only. Okay. If the width is increasing, that means the barrier potential height is also increasing. It is very difficult for these carriers to move from one side to the other side. That means hardly any current flows through the circuit due to the diffusion. Only very little current, because here in P type, if you can see, some minority carriers, that electrons may be present which are generated due to electron hole pair generations. Those electrons, they can move through this due to the drift of this applied electric field, and hence we are getting a very small current which is due to the minority carrier transport, and this small current is known as reverse saturation current. Let us analyze one more situation. Here this is you and your friend. You are standing at a distance x unit from each other. Because of this pandemic, now you are supposed to maintain a social distance, right? And to maintain a social distance, you have to increase the distance among you. Let the increased distance is equals to x plus y. How can you increase your distance? Obviously, you have to move far from each other. This is the same thing happens for the energy band diagram in case of a reverse bias condition. So this is the equilibrium condition when there is no bias applied to the PN junction. Here the formulable is aligned on both the sides of the device. Now we are considering reverse bias. Reverse bias means this V0 will become V0 plus VR. If V0 is equals to V0 plus VR, then this distance will be changing from EV0 to E into V0 plus VR. Which one is more? This E into V0 plus VR. That means this separation is increasing. Like the same thing I have shown you. So if you want to increase this separation, what will be the relative motion? This should go up and this n-side energy band should come down. So this should go up and this energy bands, this should come down. Earlier the formulable was aligned, now it is different for both the sides. For P side I am writing this as EFP. So this has moved up and this side should come down. So this has come down, and at the junction this label should be continuous. So it is starting from here and ending over here. Same thing happens over here. Now this is the junction with width W, and this value is equals to EFP minus EVP. Here it is ECN minus EFN. From here you can see the relative displacement between the bands is equals to EVR. Earlier it was EV0. Now it is EV0 plus EVR. So the relative displacement is equals to EVR. And relative displacement we can find it from here, because earlier the formulable was aligned. Now these are separated by an energy equals to EVR. So the energy separation between the formulables on P side and N side is equals to EVR. What is the value for this separation? ECP and ECN. Earlier it was EV0. Now it has increased to EV0 plus VR. Here you can see the energy separation is much large compared to the forward bias condition, and hence in case of reverse bias it is very difficult for the carrier to move from one side to the other side. So today we have discussed about the forward and reverse bias for PN junction diode and the energy band diagrams for both the conditions. In the next class we will look into the voltage current characteristics or VI characteristics for PN junction diode. Today we will stop here. Thank you all. If you like the content, please press the like button, and also don't forget to subscribe and share the channel link with your friends. Thank you all.